Hi, everybody. Welcome to day 2 of the workshop on optimizing the effort of others. Happy to have you here. For those of you who are new and just joining us, let me just say a quick word about the workshop. So what we're doing in this workshop is we're going over areas in economics and computation that have been somewhat separate until recently, but sort of share this common goal of incentivizing other people, agents, to exert effort on our behalf, either through sort of direct compensation, as in contracts, or by designing the decision rule in a way that aligns incentives like incentive-aware machine learning or algorithmic delegation. And so the idea of the workshop is to go over all these different areas, find commonalities, sort of start discussion on what's similar and what's different. So this morning, we're going to start with 2 talks focused on scoring rules by Jason Hartline and Yifan Wu, both from Northwestern. And so it's my great pleasure to introduce Jason Hartline, who will kick us off. Jason, go ahead.
All right, thanks a lot. I'm going to be talking about mechanism design for the classroom. I think this is a really exciting domain for algorithmic mechanism design to have a big impact, an impact that we care about a lot in academia. And I'll be, it's the overarching motivation and the underlying fundamental foundations that I'll be talking about is questions of optimizing scoring rules. This is joint work with Yinkai Li, Liren Shan, and Yifan Wu, and this is something we've been working on for a number of years now and has really, I think, turned into a really outstanding area of inquiry. So I want to give you the informal program that we're considering here. So we're going to be optimizing over scoring rules, the incentive for effort. Okay, so that's going to be looking at if we take expectations over an unknown state and over a posterior realization that the agent might have from exerting effort. So if you exert effort, you might learn more about the distribution of state than you had before your effort, your prior. And we're going to be optimizing the difference that the agent receives from the scoring rule when they have a refined posterior from what the scoring rule would have given them with their prior. Okay, and this is capturing the incentive they have to actually put in effort to refine their prior to get a posterior. Okay, we're going to optimize subject to some a standard constraint, which is incentive compatibility of the scoring rule. And in the literature on scoring rules, this is called a proper scoring rule. So we'll adopt the terminology from the field of scoring rules. But it's the same thing as truthfully reporting beliefs. Okay, but the agent also has another dimension of strategy, which is how much effort do they want to put in? Do they want to put in effort or not? So that's going to also be in this program. And we're going to, one reason I think that the literature on scoring rules hasn't really shown much difference between scoring rules is because they haven't normalized scoring rules by imposing a constraint like the scoring rule is bounded. Because if you just care about optimizing effort, well then scale up the scoring rule to get the difference from reporting from the prior to the posterior to anything you want, and then you've got a scoring rule that incentivizes that effort. So this optimization problem is not going to be interesting unless we sort of normalize the scoring rule in some way that forbids you from just scaling it up. Okay, and so in this space, and I'll present a detailed model in a second, but I just wanted to give you just an overview of the results. So we'll look at the situation where the state is single dimensional, and here the optimal single dimensional scoring rule is the agent is going to just tell you which side of the mean, the prior mean, the posterior is on. Okay, and once you know which side the mean is on, you're just going to have a linear score as a function of the state. So if you say that you're on the high side of the mean, you're going to have a linear score which is higher for higher states. And if you say you're on the low side of the mean, you'll have a linear score which is higher for low states. Okay, and here's a picture of what that looks like. And here I drew it for an ex post bound of between 0 and 1. So I require scoring rules to output always between 0 and 1. And then if you see the prior mean here, if the state is on one side, we get scored by one linear function. So when I draw the state, I evaluate this upward sloping linear function if I'm above the mean. And if I'm below the mean, I choose to be evaluated in the lower sloping function. Okay, and these are linear functions, so the expected value is exactly equal to the value on the line if I have a belief. Okay, and so given my belief, I always prefer the higher of the two lines given my belief, and so that's why the utility that we obtain as the agent in expectation is going to be the upper contour of these two linear scoring rules. Okay, and we also see the bound is going to hold because if you choose below the mean here, then the worst case is the state is 1, and then you get a score of 0. And if you choose below the mean, the best case is the score is 1, and so we have scores bound between 0 and 1. And the same holds for the other side. Cool, so I think the main interesting result in the paper is actually the multidimensional case. So what happens if the state is multidimensional? And then the optimal, an approximately optimal multidimensional scoring rule is just look at these single-dimensional optimal scoring rules in each dimension and take the best one after the agent realizes their posterior. So they get to get their signal. They get to essentially see which dimension is most surprising. And they'll choose to be rewarded only for the most surprising dimension, which gives them the highest score for having done the effort. Okay, and this actually, one of the reasons why I really like this theorem is that it contrasts with what everyone does in practice with multidimensional scoring rules, which is in practice of multidimensional scoring rules, they will sum them up and average, essentially. Okay, and you can show that that is a linear in approximation. Okay, whereas this optimal one is a constant approximation to our approximately optimal max over separate is a constant approximation. Cool, so that's sort of a glimpse of the results we're going to go into. I now want to take a detour through some motivation, how we got here, why we think this question is super fundamental to theory of computation. Okay, so my motivation 1 is mechanism design in the classroom. That's also the part of the title of the talk. And so here's my sort of high-level view of algorithmic mechanism design. Over the years, computer science has gotten really good at understanding how to get these things, these computers, digital computers, to do really great computation. But our techniques are super general, very robust. And can we apply the same sensibilities to understand how to get computation in the wild to produce good outcomes? And that's really the overarching goal of algorithmic mechanism design. And the fundamental building block of computation in the wild is local optimization, okay? Which for mechanism design is strategic behavior a part of the agents who are part of the system of computation you're trying to get to a good outcome. So that's our goal. The classroom actually is a great example of a computation that's happening in the wild where we want to have good outcomes. Okay, and so students are local optimizers. The grader or instructor, perhaps imprecise optimizers. The syllabus tells us the rules by which all of the optimizers are going to work together to produce the outcome in the course. The students have incentives. They probably want to minimize the work they do. They probably want to maximize the grade they get. And the instructor has some goals. As an instructor, I want to maximize learning outcomes. I want to fairly assess. And subject to that, I probably would like the overall work I assign people, both the students and the TAs, to be as small as possible. Okay, so lots of interesting things to think about in this space if I view the classroom as a computation in the wild. Cool. So the basic question here, what's the best syllabus? And there are two reasons why I really like this application of mechanism design. So on the intellectual merit side, it turns out there are foundational questions that you come across if you start looking at these optimization questions, and I'll get to that a little bit on the next slide. It's also, there's great broader impact. I really care a lot about the learning outcomes I get in my classes that I teach. And so if I can do research that helps me improve the learning outcomes I get in my class, gee, everyone can learn TCS better, and that's a great outcome. And the other thing I think is really, really critical here is there's often a disconnect in trying to apply mechanism design between the theory that we do and the things that practitioners care about, okay, and what they're willing to adopt as a mechanism and whether they can adopt some of the learnings from theory. Okay, but a great thing about mechanism design for the classroom is there's no disconnect between the theorist and the practitioner, because the theory researcher, many of them are at universities teaching classes, they are the principal that we're talking about here. And they are free to choose to adopt the learnings of mechanism design for the classroom. Okay, and I think this is hugely different about most of mechanism design. And that's why I'm especially motivated for a much richer dialogue between theory and practice, looking at questions of mechanism design in the classroom. Okay, and I think we haven't seen as fast, like we'd like to be able to come up with an algorithm, test the algorithm, repeat. That really works for the classroom because I can come up with an algorithm about once a quarter, and I teach my class about once a quarter. So I can do this, come up with a mechanism, teach my class, repeat. Okay, and I don't have problems with lock-in because, which is an issue in other areas of mechanism design, because it's a new set of students each time. They have no idea the syllabus I used last time. All right, let's get a little bit into this motivation of peer grading. So one thing I could do in my class is peer grading, and let's talk a little bit about that. So agent can either, if I do peer grading, basically I'm assigning students to grade each other's submissions. Okay, and what I care about most here is, are students going to put in effort to grade the submissions? Why do I care about that? I believe that students can learn a lot from peer reviewing other students' work. And by seeing many examples, being able to tell what's right or wrong, they'll have a better perspective on their own work. Is their answer right or wrong? Are they making similar mistakes to other people? Are they writing things clearly? All of these things come up in peer review, so I think it's a great, if we can incentivize them to do the work, they're going to learn great things from it. Okay, so an agent can review a submission or not. This is binary effort. If they put in no effort, their belief is the prior. What is the prior? Well, look, they've seen the grades the TA has been giving across these submissions. They didn't look at any. So the prior should be the average grade the TA has given so far. Okay, if they put in effort, on the other hand, they get a refined belief about this particular submission, which is different from an average submission. And they can make a refined prediction about what they think the TA is going to do in terms of scoring this submission. Okay, the TA reviews the submission and comes up with sort of the ground truth state of the grade for the submission. And then the principal grades the reviews. If we don't grade the peer reviews, no one's going to put in effort. So we need to design a scoring rule essentially for incentivizing the peers to try to predict what the TA is going to do on this submission. Okay, and I want the students to put in effort, and they get a grade equal to their score for the prior by putting in no effort. So to get them to put in effort, I really need the difference between their score on the prior and the score on the posterior to be as large as possible, because we care about maximizing this difference in effort. Okay, so there are some practical assumptions that we made in this work to apply to peer grading. So when you give grades, they're between 0 and 100. Okay, for this talk, I'll put them between 0 and 1. But this is sort of a common constraint you have in the classroom setting. Unlike settings with money, we don't care about the expected grade I have all the points. I can give them out however I want. I just can't put them out. Negative points, that would be bad. And points above 100, probably bad. We have this constraint. And I'm also going to restrict the report space to the mean of the distribution. So we've got potentially a multi-dimensional rubric. And we'll ask people to report what they expect the TA to do on each of the dimensions. And this is sort of a practical constraint. If we imagine each rubric was graded like 0 to 10, right, then a usual scoring rule would say, what's the distribution, which is what's the probability of each number 0 to 10. And you can imagine if we asked students to report these things, it would be like, oh, what are you crazy? Like, we can't report these things. So we're going to restrict it to the mean. And that's actually going to make the problem a lot harder, it turns out. And if you just look at optimizing for the full distribution, these problems become more straightforward. And we'll see some of that later in this workshop. Okay, and again, I want to talk about the practice versus paper. So in practice, when people want to look at multidimensional scoring rules, they do something like average quadratic scoring rules in each dimension. And I did this in the first iteration. And I observed that the scores we were giving back were just super noisy. And then I looked at it. I'm like, whoa. The thing that everyone does in practice is just horrible. You can actually measure it on the settings we have, and it's like there's, no effort is something like a 96 out of 100, and effort is maybe better than 96 out of 100. So it's really, really bad. And so we show that quadratic and averaging is bad, and instead we show that the optimal scoring rule has this V-shaped rule, and also rather than averaging over separate scoring rules, we want to take the max over separate scoring rules. Cool. I want to give a second motivation for optimization of scoring rules. And this is going to plug in much more to fundamentals of theoretical computer science. Okay, so here is a typical thing we might do if we're trying to do optimization with data. Okay, so we've got a data set. We're going to do some analysis. And this is the thing I care about. How well are we able to analyze our data set? What is this analysis buying us? Okay, we're then going to be faced with an optimization question that is better informed with data. So we're going to do some optimization with data. Okay, and then we're going to make a decision based on, this optimization is going to give us a decision. And then we're going to use that decision in some world where the decision is getting evaluated and we're getting some payoff that hopefully, since we're more informed because we have data, we get higher payoff. So this is sort of a lot of what we do in optimization, data science, machine learning. It's a lot of what we do. Here's the thing. Let's apply the revelation principle to this process. In other words, this payoff from my decision is a non-truthful mechanism. I have to make a decision. My beliefs are my prior from data, right? And I use my priors to optimize my decision in the world. So I put a box around that thing, and I look at just the outcome of this whole process as a function of the beliefs that I got from looking at data. Well, I'm going to optimize better if I use the true beliefs. So this is a truthful mechanism. It's a truthful mechanism that takes beliefs and compares to the state. It's a proper scoring rule. So essentially, all of what we do in optimization from data is looking at either non-proper scoring rules, or if we want to take the revelation principle to it, it's looking at proper scoring rules. Okay, and so I might as well take the revelation principle. And so then my question of how do we analyze data is a question of, when are proper scoring rules good? Okay, so this is a super important question for all of theoretical computer science. Okay, one of my favorite examples, I like Bayesian mechanism design. This is a problem in this space. Okay, so Bayesian mechanism design assumes I know a distribution, which I got from analyzing data, and my optimization question is, what's the best mechanism? I then take the mechanism that I optimized from my data, and I deploy it in the world. I get some payoff, expected revenue, expected welfare, whatever payoff you like. Okay, and so a scoring rule is just a way of evaluating how well I learned the prior and was able to run a mechanism. Okay, so some interpretations of this. So as I've been saying, scoring rules are fundamental for understanding good data analysis. And an interpretation of our question, which is how to optimize scoring rules, is a way to get a setting-independent value of a data set. Okay, because if we take the second part and just optimize it, we no longer care about the world, because the world's not evaluating us. It's whatever scoring rule we decide to optimize. Okay, it's a setting-independent way to optimize how well we analyzed our data set. This seems like a thing we should be very interested in. Cool. Okay, so what am I going to do? 10 minutes left. Framework for optimizing scoring rules with binary effort. Again, we either have the data or we don't have the data. I'll show you some details of this characterization of single-dimensional effort. I will then restate this result about how the approximate upper scoring rule in the multidimensional space is just the maximum over separate scoring rules, which we will have seen previously. And I won't get into any details, but trust me, the commonly used scoring rules are horrible for this optimization of scoring rules objective. Okay, so again, our scoring rule program in English is we want to choose a scoring rule. There's a random state. If we do effort, we get a signal which refines our posterior distribution over the state, and we want to maximize the difference in score we get with and without effort. Okay, the scoring rule should be proper, and we're going to have a boundedness constraint on it. Okay, I'm going to write this in math for the question we're actually looking at, and so some notation. We'll have a prior is going to be D, the posterior is going to, if we do effort, will be G, and G is going to be drawn from a distribution. If we do effort, we get a random posterior based on the signal we get. And so it's going to be from a distribution, so the posterior density we'll call F. And then we're going to look at the realized state theta. The agent is going to have either the prior R or a posterior R. Actually, R will always be the posterior in the talk. And a scoring rule generally is going to take a distribution and a state and, sorry, that should be the report and the state. Cool. So what does this program look like? Maximize over scoring rules. First, we draw the posterior from the distribution over posteriors, and then we sample the posterior, which is the same distribution of state as if we just draw the state from the prior, of course, by laws of probability. And then we compare the score for the mean of the posterior with the score for the mean of the prior. Okay, and again, we're taking the assumption we want to design scoring rules for the mean, which is a simplifying assumption that's probably important for scoring rules in the classroom where you need to have simple report spaces. Cool. And we want S to be proper for eliciting the mean, and we want it to be always bounded that I can give them a grade between 0 and 100 in my class. Cool. So I'm going to basically talk about characterization of scoring rules for the mean. This is usually the first step in mechanism design to characterize what's possible. And then single-dimensional, multi-dimensional, and we'll conclude. Okay, so here is the characterization of scoring rules for the mean. Okay, it's without loss to restrict to what I'll call canonical scoring rules, which will be defined based on a convex utility function. And if you've seen mechanism design, you can, every mechanism is based on a convex utility function. We care a lot about the subgradients. That's going to tell us what the actual scoring rule is. Okay, which in mechanism design, the subgradients of the utility function are the allocation rule. And in scoring rules for the mean, there's going to be a normalization, which is just a mapping from states to payoffs to try to get the balance condition to work out. Okay, and notice that the normalization does not depend on, it only depends on the state, so your report doesn't matter. So for our optimization question, it's kind of irrelevant, except that it'll help us be bounded. Okay, And the scoring rule is going to be basically, we're going to be evaluating, we're going to look at this convex utility function. We're going to look at, which I've drawn here, we're going to look at the subgradient, which is going to be a line in this scoring rule. And we're going to evaluate basically the difference between the utility and the point on the line, the point on the gradient. And the score is going to be that difference between u of theta and the utility we got from the line that we chose. Okay, so we use our report to choose a linear contract, basically, and then we get evaluated by comparing our linear contract to this utility function. Okay, so this is convenient because it allows us to simplify our objective to write it as basically, once we take expectations over the state given our posterior, then the expected value is just the expectation of u, because if we believe that the posterior is r, and we're evaluated on this line, the expected value of that is going to be exactly equal to the utility at that line. Okay? And then we also have to pay this normalization term. And so that lets us simplify the objective because the difference in scores, the expected normalization term cancels. And we are just going to compare the expected utility given the distribution of our posteriors and the prior mean utility. Okay, so what are single dimensional scoring rules? So our goal is to optimize this difference between the expected mean of the posterior, the expected posterior mean, and the prior mean. Okay, so I could choose, and I have it in here in a dashed line, some convex utility function. And here's what I claim. So we'll define a V-shaped utility function to be one that's just V-shaped. And we'll say it's V-shaped at a point mu if the kink is at the point mu. Okay? And then here's the thing. If I choose a V-shaped rule with the kink at the prior mean, this is going to weakly improve. It's going to weakly improve my objective, and it's going to maintain the boundedness constraint. Okay, why does it weakly improve my objective? Well, look at my objective. The utility at the prior mean did not change, so that thing's the same. And the expected utility only increased because I chose a V-shaped thing above this convex utility function. Okay, so the objective is only better. And this is going to satisfy my boundedness constraint, because what's the boundedness constraint? Well, I look at the maximum difference in scores, which actually always happens at the boundaries in single dimensions, and it's based on the slope at the boundary versus and where it intersects the opposite boundary and how far they are from the best, the utility and the worst utility on that line. That's obviously the worst if you are exactly wrong. You say 0 and the score, the state was 1, or vice versa. Okay, and if I take this V shape, I make those slopes less, and so the difference is less, and so I maintain boundedness. Okay, so that's it. The optimal single dimensional scoring rule is V-shaped at the prior mean. Okay, one interpretation is because the contract is basically the same no matter where I am above or below, it's just choose left or right and get scored based on that linear contract and whatever the state happens to be on that line. Cool. Multi-dimensional scoring rules. So now I'm actually not going to give the details of the proof, so essentially I've already said all of this. But let's just go through it. So a separate scoring rule is I define my scoring rule to be the sum over single dimensional scoring rules. Okay, where these are single dimensional scoring rules. Okay, and to get them to be bounded, I need the sum of the bounds to be at most 1. Okay, and the approximation ratio of separate scoring rule can be as bad as linear. Cool. The simple mechanisms we're going to be showing are approximately optimal, are max over separate scoring rules. Okay, so if any dimension I, we have a scoring rule for that dimension, and it's bounded and proper, and let ui be the utility function that comes from it, then the resulting scoring rule is we're going to figure out which dimension, given the agent's posterior R, is the best in terms of utility for the agent. And we're going to just use the score of that best dimension. Okay, so I'm assuming all of these are bounded 0, 1, because then the best one's going to be bounded 0, 1. And we'll just score them based on the best one. Okay, so again, this can be implemented by a very simple mechanism. Even if you have a high dimensional space, the agent doesn't have to report their belief on all dimensions. They just pick out which one was the most surprised, what are they most surprised by, just report on that dimension. It would be sufficient. And then we'll use the scoring rule for that dimension. Because the agent also knows already which dimension gives them the best score at the time they act. Okay, and so we proved that this is an 8 approximation. I'm not going to, unfortunately, have time to go through this proof now. It's actually a very simple strategy. Gives you this 8 approximation. And you can view this mechanism, max over separate, as a high-dimensional V-shaped scoring rule. Each dimension it's V-shaped, and you pick whichever dimension you want, which is you look at these basically hyperplanes, and you see which, and so that's sort of the global structure of the, another way to view it is an inverted pyramid, basically. Cool. And the interpretation I like about this is, like an interpretation we have in mechanism design, that linking independent decisions is good for a principle. Here we're linking decisions. Okay, rather than independently scoring people in each dimension using a average of separate scoring rules, we want to use the max over separate scoring rules to link decisions across these different potentially independent dimensions. Cool. So let me talk about some of the related work. So we build on a whole bunch of work characterizing scoring rules. In fact, one thing I think is really interesting is this, McCarthy 56 work characterizes scoring rules as essentially the pseudo-gradient of a convex utility function. And then if you study mechanism design, you usually cite Roche many years later for this. And it's essentially the same result and proof. Okay, for eliciting the mean, this really nice paper does that, and we rely on that work a lot. There was an early paper in economics about maximizing effort with quadratic scoring rules. We've seen that quadratic rules aren't very good, so we are not that enthusiastic about this approach. There's a really nice paper that came out contemporaneously with our work that appeared in EC a year ago about optimization, not with binary effort, but where effort is linear in the number of samples you draw from the distribution to refine your prior. And there have been a number of works already following up this, employing this framework of maximizing incentive for effort, and I'm super excited that this is turning into a really active research direction. We're going to hear from 2 of these works coming up later in this today, actually, and so I'm not going to talk more about them. And I think a really great conjecture and thing to strive for is a unifying framework that includes all of these things, and I think that's actually pretty close. And so one of the things you might worry about is, are these modeling assumptions really critical details of the problem? And the point is, maybe not so critical, and any of these models is going to be fine, and you'll get similar conclusions, use similar techniques, and so work in any model is work on all of them. Okay, so that's what I have for you today.
Thank you so much. We have time for a couple questions. Hara.
I still cannot hear. Hello. Wonderful talk. There has been this line of work from Neyman and Ralph Garden about recently these like polling rules, and I was wondering, it's still very unclear in my mind what the connection between like these types of like logarithmic polling type of rules is to like scoring rules. So I was wondering whether you want to comment on that a bit.
You're talking about work by Neyman and Roughgarden?
Yes, I think it appeared, was it EC last year, maybe? Someone, Bo, can help me? Eric Neyman and Team Roughgarden.
I don't know this, which exactly paper you're talking about, so I couldn't tell you.
Okay, all right, thank you.
Other questions? If not, I have a question. When thinking about the application to the classroom, I mean, and maybe this is about connecting to contract design. I mean, I can imagine a situation in which I could try to write down like heterogeneity in preferences for grades along the lines of like, here's how many hours of work an extra grade is worth to me, and maybe different students are different here. And I can imagine trying to like design, somehow like reduce this down to something that looks like money, and I have contracts. If I took that approach, would that push me in the same directions as this approach, or is there some fundamental difference there?
No, you can, so these models, you can look at, actually, and it's going to connect much better to the paper that's coming next that Yifan will be presenting. Actually, so she might be better situated to answer this question. But you can introduce private types like ability into the model, and then you can, you want students with higher ability to do more work and get a higher grade, and students with lower ability do a little less work and get a lesser grade. And so that's, it's actually, many of these extensions fit, into the model. You have to do some more work to treat things like private types. And I think they're really, and you end up with results that have really nice intuitive conclusions about some of the challenges of these questions and how they impact things in the classroom.
Great, thank you. All right, let's thank Jason again.
You know how to make it open? I don't know how to make it open.
Oh. Do you know how to make it full screen?
I don't. Just full screen. All right, great. So next up, we have Yifan Wu, who will be telling us about optimal scoring rules for multidimensional effort.
Okay, thanks for the introduction, and thanks, Jason, for the talk. So Jason talked about the approximately optimal scoring rule for multidimensional report space. So that kind of scoring rule asks the student to report one of the dimensions that he thinks will give him the best reward. So you might wonder if that's a good scoring rule to implement in practice, because this is like you are giving the student 10 assignments, but the student is only choosing to report one. So the problem is with the model. So in that model, we are considering a binary effort. So that is saying, with the binary effort model, we only need to evaluate the student on one of the dimensions to make sure the student is exerting effort. So I'm going to talk about the optimal scoring rules for multidimensional effort model. And this is my joint work with Jason Hartline, Yingkai Li, and Liren Shan. We are from Northwestern University. So our motivation is to incentivize the students to do assignments. In the classroom, the instructor gives the student a set of assignments. So the student can learn by doing this kind of assignments in the problem set. But doing each assignment can induce a cost to the student. Only after paying the cost, the student can get a signal which is informative and help the student learn. So the instructor may have a value on the set of assignments that are done by the student. So in this case, the more assignment the student is doing, the less marginal payoff the instructor can gain. So we can say the instructor has a value function which might be have a diminishing return. So our goal is to design a scoring rule to optimally incentivize effort. So we model this problem as a knapsack with incentive problem. Let's see, what is the problem without incentives? So when the agent is not strategic, that is saying the principal is recommending a problem set to the agent, to the student, and the student is perfectly following the instructions by the instructor and doing all of the problems in the problem set. So in this case, the principal faces a knapsack problem. There's a ground truth, a ground set of n tasks. So on each task I, there is a cost Ci for the student to pay to look at that task. And the principal wants to compensate the agent for doing the task in the set. But the principal may be constrained by some score budget, say 1. So the principal wants to design a problem set to maximize the value. Let the value be V and the set be psi. So for example, we can consider the additive value, which is the sum over all the tasks in the set. So in this case, if the agent is perfectly following the instructions, the principal faces a knapsack problem, which we let it be algorithmic optimal, which is maximizing the value over the set, subject to a constraint that the cost on the problems in the set should not exceed 1. So here's our model with incentive constraints. On each assignment I, we assume there's a ground truth, or you think of it as an answer of that task, which is omega I from a binary space, 0 and 1. So here's the strategic agent. The strategic agent can choose any subset of the ground set to exert effort. So we're saying the agent has a multi-dimensional effort choice. So the agent can choose a set psi and pay the cost on the set, which is sum over the cost in the set. And another problem is the agent has private learning outcome. So on each of the assignment I, if the agent chooses not to exert any effort, that is saying I is not in the set, on the effort set he is choosing. So the agent has a prior belief distribution, mu I, and the prior is 1/2. So the agent, without looking at the assignment, believes with equal probability that the ground truth is 0 or 1. And after exerting an effort on the task, the agent can learn the ground truth omega I with a probability pi. So this is saying even after the student look at the task and tries, he may still doesn't know anything about the answer. So, so the possible posteriors that the student can get is 0 or 1 or 1/2. And after exerting effort, the agent reports his belief, which is a posterior belief, mu, and this is n-dimensional vector. And the agent is scored by a scoring rule, which is similarly, as Jason talked about, the scoring rule is a mapping from the agent's report and the realized state to a score bounded by 0 and 1. So we assume the costs are in the unit of the score. So the agent's expected utility is the expectation of exerting effort in the set, taking expectation with the set, and this is expected score minus the total cost on that set. So the agent is trying to choose a set to exert effort and maximize his utility. And here's the principal's problem facing a strategic agent. So the principal wants to design a scoring rule. Here's the definition of a proper scoring rule. So this is saying from the agent's perspective, if the ground truth state follows his belief distribution, from his perspective, reporting truthfully, the expected score is greater than reporting non-truthfully. However, the principal may also want to design a problem set. So if you give the agent a ground set of tasks and simply post a scoring rule on that, the agent might have to enumerate all possible subsets of the ground set, and the computation may be very hard. So we want the principal to make a recommendation to the agent, that is to design a problem set. So we define incentive compatibility between a proper scoring rule and the recommendation set. So this is saying a proper scoring rule S and the recommendation set psi, they are incentive compatible if when the agent is choosing to do all the tasks in the set psi, his payoff, which is the expected score minus the cost over the set, is greater than he is deviating to any other subset of the ground set. So here is the principal's problem with incentive constraint. Let it be with incentive the optimal. So this is maximizing the value function subject to a constraint where the proper scoring rule S and the recommendation set psi, they are incentive compatible. And we want the score to be bounded by 0 and 1. Any questions with the model? Okay, yes?
Thanks. Yeah, just a clarifying question. So the effort is binary, but there's a ground truth that's also binary, and I'm trying to internalize how to interpret. Should I think of this as like, it's like a set of true or false questions or something like this?
Yeah,
so I'm
that's
trying
right.
to run through and just figure out true, false? Okay.
Yeah, binary choice questions.
Got it. And so that the half is basically like if I don't exert effort, then it's like equally likely true or false.
Yeah,
so
yeah. So like when the agent does not exert effort, his belief is with probability 1/2, the question is true or false. And he can guess an answer in that case.
Great, thank you.
Yeah, sure.
Yeah, okay. Can you report that you don't know, that your priority
So reporting I don't know is the same as reporting the prior distribution.
Okay, so this is what you mean by reporting the prior distribution.
Yeah,
it's
yeah.
not that you pick at random between 0 and 1, it's that you give, okay. Thank you.
Yeah. So reporting, the agent can report the prior distribution, and he can also choose to guess. So by revelation principle, it is without laws to consider the set of proper scoring rules to make the agent truthfully report the belief, right? Great. Okay, so here are some related works. So for optimizing scoring rules, previously Jason talked about our paper on single-dimensional effort model. The Osborne 1988 paper talked about optimizing quadratic scoring rule with continuous effort levels on a single task. This Neyman, Norev, Weinberg paper talk about for integral levels of effort also on a single task. There's another paper which is on contract design for multidimensional effort. So the main difference between contract design and design of scoring rule is that when we design scoring rules, the agent has private learning outcome. So the principal cannot verify if the agent, so the principal cannot verify the learning outcome. But in contract design, the principal can design a reward based on the learning outcome she observes. So this is saying the design of scoring rule may be harder. Here's the outline. For the preliminary, I will talk about how to incentivize a single task. We have a bi-criteria approximation, which is to inflate the budget by a constant factor and achieve the optimal of the knapsack problem without incentive, where we use a truncated scoring rule. We also have a value approximation result, where we use the quartile decomposition technique from the auction design literature. So how to incentivize a single task? So on a single task, the single task has a cost CI to the agent, and the agent is knowing the truth with probability PI. So you may think of if the cost CI is too large or the probability of knowing the truth is too small, when the principal has a fixed budget, it is impossible for the principal to incentivize this even on this single task. So here's our theorem from the previous paper. So the budget minimal scoring rule has the following form. When the agent reports prior distribution or reporting I don't know, the agent is scored by CI over PI. And if the agent is reporting some extreme points, 0 or 1, the agent is scored by, if he answers correctly, the score is 2 times CI over PI. So this is saying, for this scoring rule, the agent is indifferent between, so when the agent is at the prior distribution, the agent is indifferent between reporting truthfully, I don't know, or guess an answer, because only with probability 1/2 he's guessing correctly. And also for this scoring rule, the expected gain from paying the cost is exactly the same as the cost. So the agent is also indifferent between paying the cost or not paying the cost. And this is the budget minimal scoring rule for incentivizing this single task. So with this kind of budget minimal scoring rule, we know that if we want to incentivize effort on a task I, the principal should have a budget at least 2 CI over PI. And one observation is that if we want to incentivize a set psi, that any subset or any single task in that set should be incentivizable by a scoring rule. So this is saying with a budget 1 in our model, any task I that we consider should satisfy this 2 CI over PI, the ratio should be smaller than the budget 1. We state computing the optimal mechanism with our problem is NP hard, even if the value of function is additive. This is, since we have a connection to the knapsack problem, this is proved by reduction from the subset sum problem, which is similar to how we prove NP hardness of the knapsack. Here's our approximation results. So we say for additive values, we can use, like for original problem, we have a score budget which is 1. If we inflate the score budget by 11 factor, we can use a scoring rule that achieves the optimal knapsack value with budget 1, which is at least weakly greater than the problem with incentive constraints. So the idea is the problem with incentive constraints, the optimal scoring rule is hard to understand. So instead, we think about the knapsack optimal, use the simpler upper bound of knapsack. We inflate the budget and achieve the knapsack optimal with separate scoring rule. Here's our scoring rule. We call it a truncated scoring rule, and you will see why. So we designed the recommendation set by greedily include tasks into the recommendation set by the value cost ratio until exceeding the budget 1. This is solving the knapsack problem. And we have a scoring rule that can incentivize the agent to pay the cost on this set psi. So the scoring rule is, we post single-dimensional scoring rules S1 to Sn, which are inflating the budget minimal scoring rule by a factor of 9s, and truncated into an interval of score 0 and 1. So we can prove this kind of scoring rule is proper. And we can also show this scoring rule is incentive compatible with the recommendation set, because when the agent has an expected score that is exceeding the truncation we're having, the budget 1, the agent may stop exerting effort. So by concentration bound, we can show the sum over the single dimensional scores is with high probability bounded by 0 and 1. So the agent has incentive to exert effort on the recommendation set. So by this kind of truncated scoring rule, we achieve the knapsack value. And you may also see this kind of scoring rule in real life, like the instructor may post a problem set with full score maybe 150, and you tell the student you are only truncated to 100. So this is the kind of truncated scoring rule. Here's our approximation results for the value. We say we can design a scoring rule that achieves a constant approximation for the principal when the value is additive. We're not optimizing for the constant ratio, so we believe this can be reduced to something less than 100. The idea is to divide tasks into 2 sets with a quartile decomposition and use different scoring rules on each of them. So the first set of tasks has a probability cost ratio greater than 22, and the concentration hold in this case. So in the second case, the concentration does not hold, so we are using a different scoring rule. So for the first case, we are using upper bound as the knapsack problem. For the second case, we're using a different upper bound, which is also the knapsack problem, but with a very small budget on the total probabilities in the set. So in the first case, which is the core where concentration bounds hold, we are using the truncated scoring rule that I introduced for the budget inflation result. We use the truncated scoring rule with budget 1. So the only difference is when we solve the problem of knapsack for the agent, for the recommendation set, we let the budget of the knapsack problem be 1/11, and after that, we can inflate the budget by 11 factor. So we can say on this ground set, satisfying this kind of threshold, this kind of property, the truncated scoring maximum is 11 approximation because we are decreasing the knapsack budget by 11 factor. For the second case, which is harder, the tail case, we are using a different kind of scoring rule, which is we call it a threshold mechanism. So in this case, the simple knapsack upper bound does not hold for this case. So we are using a different upper bound. So the upper bound is saying the total probabilities of knowing the truth in this set cannot be too large, and it should be a very small value going to 0 when the probabilities are very small. So the budget on this set, on any optimal set that can be incentivized, it should be uniquely determined by a single task in that set. So our threshold scoring mechanism, the hard part is to find the recommendation set to maximize the principal's value. So we enumerate all possible budgets by enumerating the unique task that determines the budget. And again, we do greedy by the bound on budget. And we output the set that has a maximum value that we enumerate over. So the scoring rule here is to score 1 if the agent, so the agent is allowed to make a guess. So the scoring rule scores 1 if the agent answers at least 1 assignment correctly, and other assignments, they are not wrong. So the student can answer, I don't know, but he cannot guess anything wrong. Otherwise, he will be scored a 0. So the approximation result follows by reducing the budget on the probabilities and we achieve a constant approximation by this kind of scoring rule. And one note is that this kind of threshold scoring mechanism is not proper. We allow the agent to make a guess on the 0 and 1s, the outcome. But there is a proper equivalence to that scoring rule. So in the tail case, the threshold scoring rule is also achieving a constant approximation. We also consider the principle has a submodular value function. And in that case, we are losing a e over e minus 1 factor from all of our approximation results, because for submodular value functions, we can only do it by e over e minus 1 approximation. When the agent is sequentially responding, that is, the agent may get a signal and decide if he wants to exert effort next, our scoring rule can also achieve a constant approximation. So in this paper, we consider a very special kind of information structure. So the general information structure problem remains open for us to think about. We might need more details about the distribution, and the simple quartile decomposition criteria does not work for general information structure. And that is all for my talk. Thank you.
Thank you very much. We have plenty of time for questions and discussion. Any questions? I have one to kick us off. And this is maybe getting towards the looking at more general sort of formulations of the problem. I noticed sort of throughout the analysis and the description of the mechanisms, this ratio between CI and PI comes up.
Yeah.
And first of all, am I right in like one can interpret that as something like a value per unit of effort?
Yeah, yeah.
This is like taking the role of like
Yeah.
V in a mechanism design sort of setting?
Yeah, so yeah, that's exactly the interpretation, and we also see it in the budget minimal scoring rule. So this captures how this single task can be incentivized.
Great. I guess I'm wondering, is there hope that similar methods would carry over, say beyond a binary setting, in other settings where I can interpret there being like a value per unit of effort that's sort of consistent as I'm putting effort in? Like I can imagine some scenarios that applies and some it doesn't. Is that
Yeah,
like
so
a barrier?
even if for the single, even if for the binary state space, we consider, if you consider more general information structure, that like the agent posterior may be something other than 0 and 1/2, that kind of criteria does not work. We have counterexamples for that. So CI over PI does not work for that case.
Oh, I see. So this would be something like I put in some amount of effort and I get a refined posterior,
Yeah.
but it's not, I
Yeah.
get the answer for sure.
Yeah.
Oh, okay. That's interesting. Could you give a sense of what drives counterexamples like that?
You may get a posterior like very close to 1/2, but you are still getting something that is finer than the prior. In that case, for our approximation results, the threshold mechanism can achieve better than constant. Like if you only think about the PI over CI, in our result implies the threshold scoring rule should achieve at least better than constant. But in that case, we can actually show the optimal is only a constant, like 3 or 4 assignments can be incentivized. So this is saying maybe we need more details about the posterior distribution.
I see. And that might look something like I give an answer and like, here's how confident I am that it's correct or something.
Yeah,
like that.
yeah.
That's what you have in mind?
Yeah.
Okay, great. Thank you. Other questions? Oh, great.
Hey, so since we have time, I would love to hear about what the sequential response setting is.
Oh, so the sequential response setting is saying the agent can exert an effort, observe a signal, and decide whether he wants to continue exerting effort. So we think about our threshold mechanism, which scores one assignment. If the agent answers one correctly, the agent is get to score 1. So for that threshold mechanism, the agent may stop after he observes one outcome. But in expectation, the agent may also achieve like 1 over p, the probability of knowing the truth, may achieve this level of effort. So that's also constant approximation.
Yeah, thanks. That's super cool.
Thank you.
Yeah, this made me think of a very different question. So I guess we have a lot of experience with students who exert some effort, find out an answer and think, okay, I solved the problem, and they turn out to be wrong. They thought they solved it, but they didn't. So they're not really Bayesian if they're acting like that, right? And it might be hard to fit into this model. Do you see any way to fit that into models like this?
No, but I think you might be able to fit it into the general information model. Like the agent has a confidence level 0.8. He's not Bayesian. He simply answers 1, but turns out to be wrong. I'm not sure if that fits. Yeah.
Thanks.
Other questions? All right, if not, let's thank Yifan and both speakers again.
Thank you.
All right, we are going to end the session there. We're going to reconvene back here after the coffee break, which is at 10:45.